Good morning, everybody. So last week, what we did is we worked through piecewise functions at a slightly more advanced level than we started, and that was with functions that weren't just linear. So like on this example, we have a cube root, a cubic, and then the third piece would be a linear function. So we can see here that each one of those pieces individually looks as follows. Let me kind of show you what I mean. The cube root is right down here. Our cubic function right here in blue, and our linear function with that negative slope and that y-intercept of 9 being right down there in green. But you notice they are only shaded based on the domains where they exist, where the cube root's only between -8 and -1. The cube is only between -1 and 2. And the linear is only between 2 and 10, and you can kind of see that as I zoom in down here, only between 2 and 10. So when you put all of those pieces together, we kind of create a cube root, cube, and linear function defined only in their given intervals for their domains, and that is our piecewise function with non-linear or not all linear functions. Right on, so we're going to now look at problem number 2 here. We're going to follow our directions, and in problem number 2, we are asked to first and foremost graph, and I'm going to graph each piece. And notice there's only 2 pieces here. I'm going to graph each piece based on the equation and the given domain. So my first piece here I know is linear. I know that because, 1, there are no symbols or exponents as we discussed last week, but also because when I rewrite this piece individually, we can see that it is in slope-intercept form, where my slope, my m is 2, and my b is 1. And again, what that means in context of actual English is that the slope tells us how it's changing. So our rise over our run would be 2, aka 2 over 1. So up 2, right 1. And our b value is where we begin our y-intercept. Our y-intercept is at 1. All right, so here we go, cruising over to the graph. Let's graph that right there, y-intercept of 1. Notice my intervals are going up by 1/2, 1/2, 1, 1.5, etc. as I kind of alternate between fraction and decimals. But there's my y-intercept of 1. Boom, so that's done. And then my slope says up 2 over 1. So I'm going to go up 1, up 2 to a height of 3 now, and then over 1. Again, notice each line represents a half. So up 2 really was up 1, 2, or 4 halves. And then over 1 leads me to there. All right, I'm going to do that one more time. So up 1, up 2 to a height of 5, over 1. And let me get rid of these smaller little dots that I was just using to kind of show you how I was getting that. And then I'm going to connect my dots here. Boom. Now you might be thinking to yourself, well, Mr. Benham, this isn't representative of our piecewise function. And you'd be correct. And why is it not representative? Because notice our domain exists only bigger than or equal to 1. So these x values that are less than 1 over here, where I'm kind of really quickly moving my laser pointer, are not actually existing on this graph. So let me get rid of this and say, all right, if it's only where x is bigger than or equal to 1, well, here's where x is 1. So it's really going to be everything to the right. Right on. Cool. So now that is totally representative of our piece, our first piece, success. Now let's move on to our second piece here. And get rid of that arrow so I can do the same thing right beneath. F of x, aka output, aka y, is equal to the absolute value of x. And this is for only things less than 1. So all I'm going to do here is use my little function table logic that we talked about last week. F of x table. Remember, f of x is the same thing as y. It's truly the same thing as y. So whatever points I get here are just going to be ordered pairs. And I'll show you what I mean by that in 1 second. But now let's just pick a few really easy numbers. Okay, -1, 0, and 1, and say, all right, when x is -1, f of x becomes f of -1. We plug that into the absolute value of -1, which we know to be 1. When x is 0, f of x becomes f of 0, and we get our answers pretty quickly and easily. Right on. Now what I have here effectively, everyone, is 3 ordered pairs. negative 1, 1. So that says, all right, when x is negative 1, which is here, y is positive 1, which is there, boom. Let me erase my little arrows there and show you what I mean. Negative 1, 1, x, y, x of negative 1, y positive 1, awesome. 0, 0, right there at our origin. And 1, 1 would be right here. But guess what? Keeping in mind, y'all, that as I draw this, this point technically does not exist. Why? Because remember, it's only things less than 1. So realistically, that means like as I connect these dots, that point out 1, 1 doesn't actually exist. So we would use it an open circle to represent that. Again, open circle harkens back or draws back to our days of inequalities where we had just a less than or a greater than, no equality sign. We used an open circle to represent it. Same thing would be true in this case. And we could keep going on this one if we wanted to, because notice it's everything smaller than 1, so really everything to the left is good. All right, both pieces done. Is this a function? Yes or no? Well, we know one way to determine a function is that vertical line test. So let me just draw that vertical line here. Let me bring it on across. Ready? We're good, we're good, we're good, we're good, we're good. The only thing that you might say is we're not good there. But if you keep in mind, it looks like, and it is, that it doesn't double up here. Notice x doesn't actually exist here. It does not exist right at that point. So if you kind of think back to those days of being a kid and playing that put a block in a circle or put a block in an open space game, this would fill that hole, so it doesn't break the vertical line test, thus it is a function. Last but not least, let's evaluate, actually not last but not least, but let's evaluate this function for specific values. We're going to do this rapid fire. Ready? F of negative 2 would be here. It looks like it's at a height of 2. Boom. Keeping in mind, you could also do this another way. Which piece of our function does negative 2 fall into? Well, it falls into the less than 1 category, so we'd be using the absolute value of x. Thus, f of negative 2 would be related to that absolute value of x function, so absolute value of, little substitution, negative 2 is sure enough positive 2. All right. F of x equals 6. Notice we're off the boundary here, so we're going to use our top piece. Why? Because again, 6 is bigger than or equal to negative 1, so we're going to use our function f of x equals our linear equation 2x plus 1. But we remember that x is no longer x anymore. X is what we're trying to define it as, 6. We do our PEMDAS 2 times 6 first. 12 plus 1 giving us 13. Sweet. And last but not least, where is x at, or where is this function at when x is 1? Well, that would be right there, and we can see it really right here that x is obviously at a height of 3. Okay. Last question now for real. Is this continuous? Well, the answer to that is, I'll write this in black, or no, and let me just tell you why the answer is not continuous. Well, because again, if we were to shrink ourselves down and try to sled across this, all right, we would be totally fine sledding. We'd hit a little ramp, and then guess what? It's not continuous there. There's a big break in the graph. We couldn't effectively sled across this without having to make a jump. We couldn't walk across it. Kind of a silly way of thinking about it, but it's not continuous because of that point. There's a break in it. All right, that is page number 53, problem number 2.